Okay, so in the last video, I showed you guys the sampling distribution of the slope. Now remember, a sampling distribution is just a distribution of all possible samples. So if we took many, many samples and we looked at the regression line for all those many, many samples, we could be plotting all these different slopes. So just imagine this filled with slope, 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 slope. But it would be the sample slope. And so looking at all those possible slopes, it creates this sampling distribution, okay? Now there's a new kind of picture I want to show you that actually ties into the conditions that we have to meet for inference. You know, we always have to look at conditions when we're doing a significance test or a confidence interval. So the idea here is that I could draw like another graph almost, and I can look at certain GPAs, because remember, that's my explanatory variable. So let's say I look at a GPA of 2.0. Well, if the average GPA of looking at all the 2.0 GPAs, we could look at all of the different response times. Well, all the different response would be the ACT. Let's say the average response variable for ACT would be 17, meaning that for all people that have a 2.0 GPA, the average ACT score is 17. But that's not going to be the case for all people that have a GPA of 2.0. That might be the average, but that might not be what everybody gets. So if the average ACT score is 17 for those who have a GPA of 2.0, we might see that the ACT scores follow a normal distribution. So if we drew that on the picture, though, it's kind of like a normal distribution that goes this way. Okay, this is not going to be very good drawing. But just hang in there with me. Now, I could also look at other explanatory variables, such as maybe a GPA of 3.0. Okay. Well, if I'm looking at all the 3.0 GPAs, I might want to go back and look at all of their ACT scores and see what the average ACT score is for people that have a 3.0 GPA. Well, that average might be a little bit higher. Maybe that's around, I don't know, 22. Okay. Well, again, looking at all people with a GPA of 3.0, those ACT scores are going to vary according to a normal distribution. But the average might be 22, some might get higher, some might get lower. Well, we can again put that on our chart. Well, there's the average, but then they follow a normal distribution. And we could keep going, like maybe a 4.0 GPA. All the 4.0 GPA students, if you look at their GPA, the average ACT score, maybe that's, I don't know, like 30. Okay, but again, those scores would follow a normal distribution because not everybody would get a 30 on the ACT, even if they have a GPA of 4.0. But what these are is this is the mean response. This is the mean response variable. This is the mean response variable. Okay, y hat is the response. Okay, so what happens if you look at what I'm drawing here is, yeah, I've got all these variables, and these are all supposed to be normal curves, but what you see is there's a line that fits through these, and so we call it the mean response variable is equal to the alpha plus beta x. This is the true population regression line. Okay, now my picture is really ugly, so I actually do have one hiding underneath here. So let me erase this and show you the one in the book. That gives you a little bit better of idea of what I was attempting to draw. Okay, so I was attempting to draw this. All of these down here are your explanatory variables. But when you look at one specific explanatory variable, there's multiple response variables for that, but those follow a normal curve. But what's interesting is if these conditions are met, yeah, there's all these curves and they create the population line, but they all follow the same standard deviation, which is why it says for a fixed value x, the responses y follow a normal distribution with this same standard deviation. Okay, so that leads us into the conditions. You know that every time we've done a significance test or a confidence interval, we've had to do the plan step, which is checking the conditions. It's usually been random, 10%. And the last chapter we had the large counts condition instead of the normal condition, but it's usually been those 3 main conditions that we have to check. Well, it's a little bit different for regression. There's a little bit more that goes into it. As you can see, this picture is quite complex. So I've actually made a little acronym to help you. We're going to say check liner. Okay, not linear, but liner. L stands for linear. In order to do a confidence interval or significance test, the actual relationship, actually I think I have this pre-typed out, hey. The actual relationship between x and y is linear. So when you look at your sample data, you're going to basically make a scatter plot, and the scatter plots usually look something like this, but if it's going in that linear direction, then you have satisfied the linear condition. Because remember, we're trying to show that the true population line is indeed linear. We can't keep going if it's not linear, okay? So we would say, you know, GPA versus ACT is approximately linear. And I'll go through this all in another example in a second. The independent condition, this is kind of where the 10% condition came from. We just want to show that individual observations are independent. And this is where you're going to check the 10% condition anytime you take an SRS. So what I'm saying is when I'm taking a sample, say with ACTs and GPAs, that one student's GPA and ACT is not going to affect another student's GPA or ACT. This independent factor needs to be in there. We also have to check normal because we are looking at a sampling distribution that's normal. So to check normal, we say for a fixed x, y varies according to a normal distribution. That's kind of what this picture is showing up here, that the response variable follows a normal distribution. And there's actually an easy way to check that. And what we're going to do is we're going to look at a histogram of the residuals. And I'll show you an example down below. But as long as the histogram of residuals looks approximately normal, or we could actually do what's called a normal probability plot of the residuals, then we have satisfied the normal condition. Another condition we need is equal variance. And that again ties into the standard deviation, that the standard deviation is the same for all values of x. So the way we say that down here is the standard deviation of y, of all the response variables, we'll go ahead and call it sigma, is the same for all values of x. All of these standard deviations are the same. So the way we do that is we do a residual plot. And I'll remind you guys how to do a residual plot. But a residual plot, you just want to make sure you see even scatter amongst that residual plot. And then the last one is an important condition. We've always had this condition, a random sample. We need to make sure that there's a random sample or a randomized experiment when we're collecting our data. So when we're doing these tests, we now have 5 conditions we have to meet when we're dealing with regression. So let me go ahead and show you what it looks like for the example where Mrs. Blair took from GPA versus ACT. So in order to look at linear, we want to see if the scatter plot of GPA versus ACT is fairly linear. Well, to do that, I'm going to go back to my calculator. Oh, sorry. I'm going to go to my calculator, still the wrong screen. There we go. And if you remember, I have the data already in here. Here's GPA, here's ACT. So in order to know if it's linear or not, we're going to go to a scatter plot, which is the first option. We want to do the list 1 versus list 2. We're going to do zoom 9. Now there's a little bit of a bump, but overall it's heading upwards in a fairly straight pattern. Okay? So here's what I say. L, linear. The scatter plot of GPA versus ACT is fairly linear. And then what I might do is over here, just draw a little rough sketch of what it looks like. Okay, not the greatest sketch, but there you go. There's an idea of what it looks like. And I'm showing the reader that I have checked that it's linear. Okay, the next one is I for independent. So here's what I would say for this. Random samples ensure that individual observations are independent. That's an easy way to just throw in, like, just use that wording, and you're kind of saying it in the way you need to. Because I took an SRS, I'm going to say 9 is less than or equal to 1/10 of all the seniors who took the test last year. So this is the place where you have to add in the 10% condition if you took an SRS. If it's an experiment, you don't need to worry about it, but if it's an SRS, you need to put the 10% condition. Okay? Now again, if we're using a normal distribution, we have to check the normal condition. I said above, to do the normal condition, you want to look at a histogram of the residuals. So here's what that looks like. Well, in order to get the residuals, if we run, and we already did this earlier, but if we run a linear regression test, option 8, and you tell it run the linear regression on list 1, list 2, every time you run this, it automatically stores the residuals for you. So I just automatically run the test so that I know the residuals are stored. I go back to stat, scroll over to calc, no, not calc, stay on edit. I'm going to go to list 3, and I'm going to put in my residuals. So if you remember, you go second list, and you can scroll down, and it saved your residuals in this residual list. If you hit enter, there's all the residuals from the regression line from the data we have inputted. So to look at a histogram of the residuals, we're going to change it to a histogram instead of a scatter plot, but I want it to be a scatter plot of my residuals, which remember was in list 3. So I'm going to go zoom 9, and remember we never want to use the example here. So I always go to my window and I change my window settings. I'll maybe go down as low as -5. 5 is a bit high, so I'll go just to a regular 5, and maybe I'll do it a scale of 2. If I hit graph, now again, that doesn't really look normal, but it's, you know, yeah, this piece right here is pretty short, but I mean, it's not skewed, there's no outliers. If you don't love the way the histogram looks, you could always do a normal probability plot. So another option, I would say that this is safe to draw and go ahead and say histograms look approximately normal. I think you're fine on that. You just don't want to have any weird skewness or outliers. But again, if you want to try something different, another option you could do is a normal probability plot. It's been a long time since we've seen this, but it's this very last option. As long as the residuals look like they're going in a linear fashion, you can say that it's normal. So zoom 9 and take a look. The residuals are heading in a linear direction, so that's safe to say that it is normal. Okay. So the way I would say it here is normal. The histogram of the residuals is roughly normal, and what you want to do is draw a picture. If you remember, the picture I had was kind of like this. Okay. Or instead of histogram of residuals, you could cross that out and say normal probability plot, and you could draw the picture of the normal probability plot heading in a linear direction. Those are 2 options for checking the normal condition. Two more, we have equal variance. The residual plot shows similar scatter for all x and y values. So in order to show that, you need to go back to your calculator again. We need to look at a residual plot. So on the residual plot, remember, that is a scatter plot with the explanatory as the explanatory values on the x-axis and the residuals on the y-axis. Well, remember, my explanatories are in list 1, my residuals are in list 2. So I'll go to stat plot. I'm going to change it to a scatter plot, and I'm going to say list 1 against list 3. Take a look at the scatter plot, and there is even scatter amongst the residual plot, and that's really all you need. So when you go over here, you say residual plot shows similar scatter. Here's what the residual plot looks like. I'm just going to draw a rough picture of what it looked like, and I would say that that shows there's similar scatter for all x values. I'm going to have to stop my video here because it's going to run out, so see the next video for the last little bit.